everybody. So thank you for coming to the 3D printing workshop. I'm Kyle, the senior tech lead at UTDL. With me is Sohail and Noah, and our other companion, Kapel, is not here at the moment, but he might be coming. Okay, so he'll be coming in the next couple minutes then. But yeah, so today we're going to be talking about 3D printers and how to go about 3D printing. So I'll be starting with the types of 3D printers, how a 3D printer operates, the safety behind 3D printers, how to convert files from, say, SolidWorks or Fusion 360 to allow a 3D printer to print this given pieces, how to model for 3D printing to save time and material, especially in the design-a-thon. You will only have certain time limits to print on the printer, and if you can print a bigger piece or a more complicated piece, you want to do so in that given time. Then how to actually get the file into the 3D printer and the specifics of a 3D printer, the temperatures and time and everything about that. Talk about how some prints fail and how to prevent those, and then how to go about finishing a 3D print to get a realistic piece from plastic. So there's two main types of 3D printers. There's an FDM printer and an SLA printer. This one right here is an FDM printer. An FDM printer is just, it uses plastic like the green you see, or the green plastic, green filament, and it layers plastic layer by layer until you get a 3D object, compared to an SLA printer, which is resin-based and uses lasers to pull an object out of a tub. Like these, there's a Delta and Cartesian. These are two FDM printers. The only main difference is that a Cartesian moves in the Y, Z, and X plane, compared to a Delta, which prints using three arms, as you can see here, the 3 arms, and then it prints in a cylinder-like motion compared to a cube-like motion. And then you can see the SLA printer here. It uses this bed right here in the resin and slowly pulls the print out of the actual resin container. But the design-a-thon will be mainly using Cartesian. Come on in, guys.
Hello.
Hello. So at the design-a-thon, we'll be mainly using Cartesian printers, so the one you see in front of me. This is actually the exact model we're going to be using. We'll have about 15 to 20 of these available for everyone to use, which is pretty cool. So as I said before, we're going to be mainly focusing on Cartesian printers, since those are the ones we're going to be using, and they're the most common and easiest to use and buy. So as I said, it has a Y direction of motion, an X direction of motion, and a Z in order to print its cube-like function. It utilizes a hot end and a heated bed. So a hot end is, it's behind this plastic and behind this fan, there's an object that looks like this. So this is what's known as a hot end. So it has right here this little cube, or you can see underneath. It gets to a very hot temperature, to the specified temperature, to print and to melt the actual plastic or material that you're using. There's then these two big long cables. Those are for to actually power the heater that's in there. And there's these little blue ones, little red ones, is to thermistor, which tells the printer if the hot end is at the specified temperature that you told it to print at. Then for most of the 3D printers, there's a heated bed. So this one has one as well. So it just means that this bed right here will get to a temperature that you specify in the slicing program, which I'll show you, to allow better bed adhesion of objects on the actual print bed. And then the final component of how a printer operates is the filament. So filament is this stuff right here. It's pretty much plastic in a big long string. There's two main types. This is just depending on the diameter. There's 2.85 and 1.75 millimeter thickness, I believe. So I use 1.75 with these printers, and the printers you'll be using at the actual design-a-thon use 1.75, but we'll be providing all that just for knowledge of 3D printers. And then for safety of 3D printers, of course, the hot end, as I showed, was under here, or this component, can get very hot. PLA, or polylactic acid, is the the polymer that we're printing today, and I've printed with a lot, it melts at a temperature of 180 to 200 degrees Celsius at this point, which is very, very hot. So you don't want to reach underneath and touch the hot end while it's hot. And the heated bed with PLA will actually get to a temperature of about 50 to 60 degrees. So it's warm to the touch, but still don't want to touch it, because if you're printing with, say, there's another plastic called ABS plastic, which prints at a higher temperature. It prints at about 220 to 260 degrees at the nozzle, and the bed is required to be 100 degrees. So it'll boil water if you touch it. So it's very, very hot. So you don't want to touch the hot components. And then, of course, you don't want to touch or put your fingers in any of these links here, because they're moving back and forth, and you don't want to stop the printer to malfunction it or cause a failed print. You also don't want to get your fingers stuck in the places you don't want to get them stuck in. And then for other notes, you don't want to be pulling on the filament when the actual printer's in use, just to not cause a malfunction or a failed print. And then you don't want to leave any tools on the actual bed, because as they are metal, they will get hot, and you may even damage the actual printer itself, because this bed right here can either be, so it's mainly metal on top with a sheet called a PEI sheet. It's just a thin little like absorbent sheet in a way that allows maximum adhesion with the actual printers. But some of them can be glass, and some of them can be just straight metal. So it'll just get everything very hot, and you might damage your printer. All right, so I'm going to just start talking about how to convert files. It'll make the rest of the process of showing all the documents better and easier. So when you're in, say, SolidWorks, you work in parts in SolidWorks, so you'll have a part instead of a cube. And SolidWorks or Fusion 360 save these as part files. These allow CAD files and CAD programs to understand the dimensions, the weights, or whatever you CAD into it. So to convert this into a file in order for a 3D printer to read it, you need to you want to save it as a different file. So you want to go to Save As, and then this will come up. And then right now it's saving as a part, and that's what CAD programs save it. So you want to click that and scroll through until you see STL. An STL file just allows a part to be understood by a slicing program that a printer understands. So after saving that, you will be able to convert it into what's known as G-code. So then in Fusion, it's the same sort of thing. You can go to File up here, or you can go to the file within Fusion 360, and you want to export your piece. So you get your name of your piece, and then when it says type, it's saving it as Fusion 360's equivalent of a part file. When you go into here, you're able to save it as multiple different file names and file codes. So you want to go to STL file and save it as an STL file. So then after you export that, you're able to manipulate that into a G-code file that the printer reads. So now that you've seen how to convert part files, something that you've actually made or created in the digital workspace, into let's call it like a medium file. So it's the file between a part file that you had and the file that a printer reads. You need a program called a slicer program, as I've been talking about before. A slicer program takes this STL file and converts it into a G-code file. A G-code file is what a printer reads. It pretty much makes this piece into a continuous path that allows a printer to register a Y, X, and a Z location in order to print this given piece. So the one that's most commonly used and easy to use is a program called Cura. So Cura is a free program, so you'll have access to these slides, but if you Google Cura download, it'll probably be the first link. It's by Ultimaker. And then going through that, you're able to convert your files into G-code. So when you open up Kira looks like this. It's got a build volume, so that's this cube here, and it's actually, I've registered it to my printer. See in this top right corner? So this is a Prusa i3 Mark II. So when Kira first opens, it'll ask you what printer you're printing in, printing with. So when you select your printer, it just enables the build volume, so that's the components in which the printer can actually print in, because most printers have different volumes in which you can build at, and it specifies it into here. It also allows, and the program knows, the maximum temperature that your printer can print at, and if it has a heated bed or not. All these variables allow in the settings that come up to be able to be changed. So going into here, you can choose different materials, saying ABS or nylon or PLA. PLA is the easiest one to work with, and is what pretty much 90% of people and makers use with 3D printers. Going on the right-hand side, you have all your settings in which you can use to use a 3D printer. So layer height is one of the big ones that affect a 3D print and how it prints. So a layer height is, if you look at any of the components here, it's the height at which the plastic is laid on each kind of layer. So it's just the building up height that the printer builds before going up on Z. So yeah, I'm gonna pass this around. So the main focus is on 3D printers can usually print with good quality is like a 0.05 to 0.01. That's a very detailed print. The ones that you have in front of you are printed at 0.15 layer height, so it's very thin. And printers with the nozzle that's given, like a stock nozzle, can usually print up to 0.3 millimeters. So that's just giving a height variation. And the difference in height makes the difference in how long your print is going to take. So the rockets that you see in front of you, they printed in just over an hour. So I'll say an hour and 15 minutes. But if they were printed at, say, 0.3, it may have only taken 35 minutes to print. So the height changes the quality that you see and decreases the amount of time that a print takes to print. Another main one that is main to focus on is infill density. Infill density is the amount of plastic that is printed within a given object. So in those rockets, they're not hollow. They're not just a shell going up in the side. There's actually cross-hatching inside of it, which is
It's like a honeycomb.
yeah, it's a honeycomb on the inside. Is there a marker?
Yeah, you can see it in this piece. It's not actually solid, but it's hollow.
So that's our support material. Yeah. So on the inside, go over here. There's the main object, right? So that's what a printer would do as a first layer, and it would fill the bottom, as it shown here, would be completely filled in, just to make a base. But after the initial height, it would start printing on the inside, something like that. So when you get to the top of the object, or the top of, say, a cube, it has something it can print on at the top layer. It's not printing in the middle of air. It has these like supports that are on the inside that might have to cross. Now those are just different shapes, and going to settings, you can either do straight lines, diagonal lines, or honeycomb, which are octagons all along it beside each other. But infill density is how much percent is filled with plastic. So right now it's set to 10%. So it would be on the inside of an object, 90% air and 10% plastic. So for structural integrity, of course you'd want to go higher up, but for models like you see in front of you, none of them are printed at more than a 20% infill. And if you try and squeeze the rockets, there's no way that you're going to be squishing it, even though it's at a 10% infill. And actually, a good comparison is this guy right here. This is a 100% infill piece, and it's just solid plastic. So another great one is the printing temperature. So the printing temperature is different with every plastic that you're going to be printing in. So PLA, like this guy, I usually set it to about 180 to 220. That's the printing range. But every 3D printer has a sweet spot, if you're to call it, that it likes to print at. So this printer likes to print at 215 degrees, as I have in the settings. That's just the optimal point at which my printer gets good layer adhesion on the base, and layers actually stick to each other, and the print looks good overall. The next one is building temperature, like the building plate. So that's the base right here, and what temperature this is at while printing. So PLA prints at 215 degrees here, and likes a bed of about 50 to 60 degrees. So I have it set for 50. But if you're to change plastics, so I printed in ABS, as shown in the other plastics that were up there. Prints at about 250 degrees at nozzle, and likes a bed temperature of 100 degrees. For most of these temperatures, you can just Google whatever plastic you're working in and we'll give it to you. Or on most of the filament spools, it'll actually say on the side the 20-degree temperature range that they recommend you printing it in. The next one would be printing speed. So that's this guy right here. Printing speed is how fast your nozzle is moving in comparison to laying the plastic. So you don't want it to go super fast, say at 100 millimeters a second, but you also don't want it to go super slow at 2 millimeters a second. Because if you're at 2 millimeters a second, that just increases the length of your project dramatically. And if you do it 100 millimeters per second, your print quality isn't going to be that good. It's going to be stuttery, you're going to have bumps within the layers, and it's just not overall going to look as good. Usually people print within 40 to 80 millimeters per second, just giving you a good variation of good quality, high quality prints, but able to get to a speed which is fast. So this dragon right here was printed at a layer height of 0.1 millimeters, or 0.01 millimeters, sorry, and was printed at 65 millimeters per second. And the quality of the dragon and the layer lines, you can't see because it was printed at accurate and good settings. And then another key support piece here in these settings to go over is support material. So support material is what an object that overhangs. You can't just print in midair. Yeah, you just can't print in midair, as a printer will have nothing to lay the actual plastic on. So for the Iron Man top of the helmet, no.
Yeah, we can pass it.
Who has the top? There it is. Awesome. So, thank you. This is the top of Iron Man's helmet right here. So it's a dome-like structure that is used for the helmet. So a piece like this, you can't just print the top in midair after it's printed all this height. So you need what's called support material, which is this stuff right here, which prints under the overhang, allowing the actual object to rest on. So this will just, once the print is finished, we tear this out and it'll be tossed out and just garbage for the rest of the print. But it's used in order to actually make your 3D prints, and it's very necessary for certain objects. So say Benchy here does not need supports because it's got proper pieces on it, and it has curves and arches and allows it to not use support material. But say Iron Man mask here, if it printed standing up like this. So it's fine all the front features because it's pretty much printing straight up, but when you get to the back, these top pieces right here are overhang, which means the printer would print in midair and it would have nothing. So the plastic would just come straight out of the nozzle. So Iron Man was printed with support material coming straight up here, allowing the actual mask to have something to print against so it wouldn't topple over or fail. And you can enable that for different features. So you can either have that only support material touching the bed and up, or you can have it print everywhere. So if I were to have it print everywhere, over the eyes, there is it's not touching the ground. It would be touching the other side of this. So if I said only the ground up, it would only print here. And if I said add support everywhere, it would add it here and under the eye, in the eyes, as there would be an overhang.
Question.
Yes.
So let's say you made it from the ground up. How would it print the eyes in that case if the eyes are extruding towards the other side?
Good question. Thank you. So there would actually be support material coming up from the build plate. Put it here. Coming up from the build plate, going up to here. And then since the eyes have no build plate underneath it and mass is in the way, it'll actually use support material and put it on the eyes right here and just it would be a small structured material that goes up from the bottom of the eye to the top of the eye. It would be easy enough just to poke it out afterwards and take it off, as it's not super, doesn't have a lot of adhesion to the actual mass plastic itself. That makes sense. Yeah. So it'll actually utilize the piece it's making to use the bottom support for the rest of the support material. And then a final one to talk about in Cura is build plate adhesion. This is very important for different types of prints. So there's skirt, brim, and raft. So this build plate adhesion, being the three of them, we'll talk about skirt first. Skirt pretty much just prints the object. I'll go back over to the board for this. But it prints the object on, say, so we have this is our bed of our 3D printer. So we have, say, our object. Let's just do something like this. So we've done this U shape. A skirt will come out, and before it does the initial layer of the 3D printer, it'll come out and do an outline in plastic, just one layer line thickness, and then it'll start doing the 3D print. This skirt just allows the nozzle to ensure you visually that the plastic is going through the nozzle and is sticking on the actual build plate itself. So if there was no plastic coming out during the skirt, you can stop the print, ensure that the plastic is correctly aligned or correctly coming through, and then continue with the print. Next one would be a brim. So say we had, I do. So let's say we printed Rick here. So Rick would be printed standing straight up like this. Now Rick's feet have a very small surface area. So when Rick is printing after his 13 or 14 hours that we printed in, I would want to make sure there's proper bed adhesion so that he's stuck to the bed for the entire 14 hours. So I don't trust his feet. I don't think he'll stand up for the entire 14-hour duration of his print. So I would create a brim. So a brim, there's Rick's feet. A brim adds surface area to the first layer of your print. So Rick's feet would look like this, but with a brim, it would add circles like this around his feet, and all this would be plastic. So he's pretty much added a lot of surface area to his feet, allowing him to have a better grip adhesion to the actual build platform. And once the print is finished, since this is only one layer thick, it's got a maximum of 0.3 millimeters, it's going to be able to torn off, or use a little pair of scissors in order to cut it more accurately around his feet. So that is a brim. And then a raft. So a raft is a little more complicated than a skirt or a brim. Skirt and brim are pretty similar. One's just touching the object and one is not. With a raft, this allows you to print uneven surface areas on the build platform. So say we wanted to print, so looking at the object from its side, these would be completely random, but we wanted to print this wave on the build platform for whatever reason. The raft would come in from the build plate, now looking from the side, and print material like this on the platform and straight up, and adding layer lines. It's pretty much support material, but it's holding the actual object off the bed, just to allow it to make sure you have enough surface area on the bottom touching it, and it's supporting the piece at a proper position and not enabling you to continue with the rest of the print. So those are the main features in Kira to understand, and once you actually enter into Kira, those are really the only settings I've ever changed, and I've done about 4,000 hours worth of 3D printing, so it's very accurate and you can get very good and dialed in prints just changing those couple of settings. So the next thing we're going to be talking about is modeling for 3D printing. So at the actual design-a-thon, as I said earlier, you're only going to have 24 hours of building, and in that 24 hours of building, you're going to have specified time slots at which you can 3D print. Say it's between an hour and 2 hours. So you may only have a 2-hour time slot for each piece that you want to 3D print. So ensuring that you can get the minimum amount of time for your piece allows you to print a bigger piece or a more complicated piece within your time limit. It also, when you start printing by yourself, decreases the amount of support material that you need, or decreases the amount of material that you'll be using, thus saving me money, saving the amount of material that you have, allowing you to print more objects. But yeah, the biggest factor for the design-a-thon is the time. So there's this piece that I created in Fusion 360. It's just a bracket with 2 holes and this overhang. So there's a couple geometries that you could actually print this. So moving over to Kira, I can drag in my STL file, and all of a sudden I have this part in Kira that I can play with, and I can model and get ready for the 3D printing. So right here, if I were to model it in this orientation, it would have good bed adhesion because there's a lot of surface area that is actually touching the bed. The holes will be properly aligned and will not have any drooping or overhang due to the heat of the 3D printer. However, I have this overhang right here. Now I can fix that just by adding support material and adding support material to the piece. So adding support material, if we go into layers on the right hand side, that just allows you to see from the object to what each layer will look like. This blue material right here is the support material. So going into that, we can see from the underneath that it'll do a squiggle line underneath to hold that material up, much like the Iron Man top hat here. It did the same support material underneath. But looking at it, I don't want to waste the material or add the time that this will take to print at this location. So using this piece as rotation tool on the left hand side, I am able to rotate the piece 90 degrees to a better orientation. Now, I don't need the support material in the overhang. So I can take the support off. It still has good surface area that's in contact with the build platform, so it's able to actually hold on the build platform. However, now I have the issue with dealing with these holes. So printing like this, it will print well. All the sides and the overhang will be fine. However, these holes won't print perfectly circle. They will print the bottom 3/4 of the circle will be fine, but the top will actually droop in a little bit and come either a little flat or droop in a little bit. So your circles are no longer perfectly the dimension that you wanted them to be. So to fix those circles right here, you would want to 3D model in little eye drops. If you make them look like little eye drops, that way when it goes and it prints over the top of the circle, you're accounting for that droop, and when that droops in, it'll come to near perfectly the circle that you want it to print in. The only thing is, when you're creating these eye drops, they're custom for every circle. So when you go into, say, Fusion 360, and you have your eye drop, you can create a sketch on the one hand side, a sketch, and then you can extrude the top of these holes. Now, depending on the diameter of the circle, really depends on how big the eye drop is. So these holes are actually about 3 millimeters. So I've gone up maybe 0.5 millimeter to 1 millimeter just to account for that little droop. But if you're doing a bigger circle or a bigger hole, you'd want a bigger drop to account for the drooping. Yeah, so that's how orientating a piece can actually save time and save plastic, and just in the making sure that you're modeling in mind for these orientations in the piece to account for drooping or how a printer actually prints. So now there's this piece. So what if I wanted to print this piece? It's a box that has a cutout in it, but I have this little strip that's running along the one side. So there's different orientations I can print this in, right? I can print it standing up like you see here, and I can add support, click the support material button, and it will automatically add support material from this line right here straight up to hold this piece in line with where it's supposed to be. However, that's going to increase the amount of time that this guy takes, because support material prints at a lower speed and a slower speed than the actual rest of your print. And it's also going to be tedious to get off when you finish the print and you want to get the 3D material off, because it's between two pieces and the piece is quite large. So to go about this, I'll actually show you quickly what it would look like. So there's this piece. So there's the overhang on the one hand corner I was talking about. So we could also print it like this, right? In this orientation, we have a great surface area touching the build plate, which allows us great bed adhesion. However, we still need to enable support. Still adding up support in this smaller plane, but it's still adding support, and you're still wasting time that could have been made for printing actual piece. So there's, and then if you were to print it, say in this orientation, yes, now this piece no longer needs support material. However, if we click here, all of a sudden, the entire inside will need it because of the top plane. So to get around from using support material on this object, we'll actually, I would create custom supports. So knowing that your piece is going to need supports at some point, I would create little tiny geometry lines. So they're only about 1 millimeter thick and 2 millimeters wide, but these custom supports all of a sudden are supporting this material. Now you might say, well, Kyle, there's overhangs right here, and those aren't getting proper support when you're printing. So since a 3D printer prints continuously per each layer, I know that it's going to be, usually it will start in one of the corners and it will continue each layer up from that point. So going across here, it'll print from here over in this direction. So really, the printer only has to deal with these little tiny overhangs. A 3D printer is capable of printing small overhangs, maybe up to 1 or 2, maybe 3 centimeters if everything is dialed in right. This fan that you see in the front cools the actual printed plastic as it's printed. So it goes from solid to a malleable plastic, back to a solid plastic within a second after it's printed. So it's actually able to hold something like this over those short distances. And once the first layer has been gone around, all of a sudden that second layer has a platform at which it can print on. So going into Kira with our newly created piece, we can orientate it in the geometry that we planned with using the support material, and all of a sudden we do not need the support material, as the piece will be able to hold itself up. So that's how I would model and keep orientation with geometry.
So from your experience, like the way I'm envisioning it is that the support material would be easier to remove. Would you say this would be as easy to remove, or would it
So with support material, there's this piece right here. So this printed with the support material holding it upright. So this support material, if you were to pass it around, if you try and squeeze the bottom, it's very tough and it's very difficult sometimes to get it off of big surface areas in which it's printed in. That's when you use different types of tools in order to pry and trying to get it off. With something along the lines of this guy, I know that these dimensions are only 1 millimeter by 2 millimeter. So I can actually, once it's printed, I can take my little cutters and I can actually just snip those 6 big pieces off, and in a couple seconds there's no support, and it's ideally the exact dimensions I want it to be with, even if I were using support. So yeah, this is a pain to get off sometimes, so utilizing this method just saves you a lot of post-production time as well. So actually, if you want to pass that over, try and break the support off. It's very difficult. Yeah.
I have a question. Wouldn't the overhang create the same problem that the circle is doing?
So that's another good question. Yes, there's the overhangs. Some of them are, depending on the length, creates different types of droops or different types of overhangs. With circles, it's because you're going over it multiple times. It's just the heat that kind of brings it down. Since these are going over a longer distance and they're straighter, there might be your first layer or first 2 layers might be drooped down, but because the printer has something to go over the second time, it will create those layers pretty much perfectly straight. So say those layers have drooped, you can actually reach into the piece and take them off, those 2, maybe 1 or 2 layers, and we're only talking about 0.1 of a millimeter, so those we'll be able to, but because there's material already there, the 2nd, 3rd, 4th, 5th, maybe 15th layer will have straight lines to go across. Does that make sense? Okay. All right. So let's talk about some common failed 3D prints. So getting into 3D printing, fails in 3D printing do happen a lot. I've had my fair share of 60-hour print. I'm 45 hours in, and the print slides, it's garbage now. Can't fix it. Once a printer starts printing to the time it's finished, you don't want to have any fails, because if it does, you have to scrap the piece and start over again. So sliding is a big factor. That's when your piece is on the build platform, and within the layers of starting to finishing, the print twists, moves, or actually slides and falls off the build platform from moving in the vibrations. That thus creates a failed print. The next one is the layers don't stick, or you're out of filament. So in Cura, we'll do the original piece. There's this piece, right? So in this bottom right corner, it tells us the actual how long, the time it's going to take, and the amount of filament it's going to need. So this piece in its current orientation, current infill, current print speed will take 2 hours and 6 minutes from the time I hit go on my printer. And it will use 7.4 millimeters of filament, or an equivalent of 22 grams. So 22 grams isn't a lot. These filaments come in 1,000 gram components, so you're able to actually check on some filaments. They have roughly how many grams you have just by the diameter of what's left on it, so you can actually visually see if you have enough filament, and you can keep track on how much time it's going to be. So you don't want to run out of filament, because once your printer runs out of filament, it will not know it's run out, so it will continue printing. And say you've printed a piece, and it was supposed to be as tall as it was supposed to be, say this high, but you ran out of filament here, the printer will continue printing, but it will print with nothing. So it will continue for a couple hours, and it'll look like this when you come and check on it next, because there's no filament attached to it.
Question?
Yeah.
If you run on film, the hot end nozzle will break, or because of overheat?
No, so it will not overheat. The hot end is this piece here. It has a heating coil right here, which allows heat dissipation. So it just keeps the exterior cold enough for everything to hold onto it. And then there's there's fans that are actually blowing on to the heating coil, the heat extractors there, just to allow it to stay at a constant temperature and ensure that it's maintaining a constant temperature throughout its print time. A nozzle, I've never experienced an overheating with a 3D printer, and my longest print was 72 hours, I believe, or just over 72 hours continuously straight. And then I took it around and flipped it into another 56-hour print within a half hour of it stopping. So I did a lot of printing after the fact. So yeah, it's just something to watch out for. Lots of them use fans to ensure that they don't overheat and stay at that constant temperature. Another one is stringing. So stringing occurs when you're printing multiple objects on a build platform, or you're using components that have printed sections where the nozzle has to jump across. Stringing occurs when the nozzle doesn't pull the filament up all the way when it's moving across an empty space. Thus you get these strings that go from piece to piece, and those aren't necessarily good to have. They're an easy cleanup because you can just use a pair of scissors or snips and a little bit of sandpaper, but you can get to the part where it might look like a failed print in between because it didn't extract the filament enough throughout its print. And then the last one, major one, is warping. So warping occurs is when a piece you've printed flat on the build plate has started to warp in one of the corners. Usually it's one of the corners of a square or rounded object, and it starts to come off the build platform, causing it to have a height increase off the actual build platform, and this isn't good, because all of a sudden, we don't have bed adhesion in this one corner. And say it's starting to warp, and it warps up 2 or 3 millimeters, yes, that's not a lot, but when we're dealing in increments of 0.1 or 0.2 of a millimeter, that's huge. So if it starts to warp up, all of a sudden, this nozzle, when it moves across, it might hit this warped up piece and knock your part off the build platform, because it's caught, hit it, and it's not had enough adhesion, so it's knocked itself off the build platform, and all of a sudden the printer is printing in midair, and you have a failed print. So to prevent sliding, you can ensure that the bed is clean. You can use a damp cloth just to make sure the build platform is clear of all debris. You can then go across with a microfiber or rubbing alcohol to make sure it's perfectly clean. You can also use glue sticks, a little bit of glue stick onto it, and ensure that it has good bed adhesion with the print. You can also use hairspray. People use just a little spray of hairspray in the area that you're printing in, or to add a little cushion to allow the actual plastic to print onto something. People use painter's tape, blue painter's tape, and they'll put a little section of that on the actual print bed itself to ensure they get a good adhesive bond between the first layer and the actual print bed itself. You can also use a raft if there's unevenness on your first layer. So then, you can, for layer adhesion, you can also increase the printing temperature that you're printing at, or the printing temperature of the bed. These just make the plastic more malleable and have a better grip on that base plate. And then, so for the lack of filament, as I showed you in Cura tells you how long it's going to take and how much filament it's going to take to use up for the print. So before you go on your printer, just making sure that you have enough filament to complete the print is one of the first steps that should be taken before you hit the go. And then for the stringing, printing at a hotter temperature will allow it to become more malleable, which might stop the stringing. You can also, in the printer settings, you can recalibrate your extrusion level, which is the amount that the stepper motors pull back the filament when shifting between pieces. This just makes sure that there's no filament at the end of the nozzle, so when it strings, it goes across, there's nothing to go out and create those strings. And then for warping, you can ensure that your bed is level. So some printers have auto leveling, which it levels the actual printing bed itself and accounts for that. Other printers have manual leveling. So those manual levels will have 4 knobs, one in each corner of the bed, and depending on the direction you twist those, will either increase or decrease the height in that corner. So you can change every angle on the build plate. So going through and making sure that those are all level with the actual nozzles themselves is crucial in order to get that perfect layer adhesion on your first print. I won't go into detail on how to do that, but if you want to learn more about that, you can talk to me after the fact, or if you Google on YouTube or go on YouTube and search up how to level my manual leveling 3D printer, there's a ton of videos to go more in depth about leveling it. All right, so how do we start a 3D print? So, of course, first step is to clean the bed, as I said, and make sure that there's nothing on the bed. So I actually have some filament from my last print, so I'll take those off, and that's clean now. Some printer beds might like it, and you might find that sweet spot is to use a little bit of glue when you're modeling. So I do use glue on this build platform. So I would apply a little layer of glue in the area that I'm printing in to make sure that it's good for printing. And then I would turn the printer on as it is starting to go on to. And then in Cura, when you have your piece like this, you're able to go into this bottom right corner and save the file. So you can label the file, and you'll want to save it to an SD card. So this SD card will now contain your G-code file that you created in Cura. So once you save that, it will go onto the G-code file, will be on the SD card, and you can take that and plug it into your printer. Once you have that, you can go into your printer and you can start preheating it. So that's just going through the settings and literally hitting preheat for the type of plastic that you're wanting to print in. And then you can go into your settings and select the piece that you want to print. So currently it's heating up, and once the bed is heated up to that 50 degrees and the nozzle underneath here is heated up to that 215 degrees, it will go through, and since this is auto leveling, it will level the bed, and once it's done the A-OK and knows what height each of the corners are at, it will start the print. And then after selecting your print and hitting the go, you just wait. You have to wait until your time is up. So the print that will start takes about 20 minutes, 22 minutes with this print. So we just would have to wait for that to be done. But we'll keep talking. So after finishing the print, you'll have the object sitting in the middle of the print bed, ready to be taken off. So sometimes you have enough leverage and you can literally just pop the actual piece off the build platform. Other times it's going to stick a little bit because you use a glue or hairspray. So using things like a spatula or a paint lifter, you're able to actually pry off your piece. Gently, of course, not to hurt the bed or damage the piece, but enough just to get enough leverage underneath it. And then sometimes that's perfect. That's enough to make a print look good, and that's the look that you want. Like this guy, this is purely just plastic. However, sometimes you want it to look like it's not plastic. It's like Iron Man over here. So after that, you would start sanding, priming, painting, and Bondo. Yes, that's a lot. But if you look around the room at the rockets, there's the original one that you have, built. You have the original 3D print. So that is strictly what the rocket would look like with no post work. And then you have the actual sanded version. So once you have the actual original one, just take a little bit of sandpaper and start roughing up, trying to get it smooth. And then you have the next stage, which is the priming stage. So I've added a couple layers of spray paint just in order to fill up those layer lines to get it to a point where you can see the highs and the lows of the imperfections on it. And then with more sanding and priming, doing that a couple times, you can get a smoother layer look. And then there should be an all-white rocket right there. So then you go to a normal base coat. So the base coat is just one color along the entire printed piece. And then after that, you can go into detailed work, where after, say, spray paints or Bondo, like which is on Iron Man's task here, it's just a sandable material that allows you to get a smooth finish. You can start adding detail work. Detail can be done in acrylic or any given paint that won't stick. The acrylic and spray paints are the two main paints that I use and makers use around the world. So also, if you don't want to go the sanding route or the priming route, you can use chemical baths or heat treatment to get rid of the layer lines. I don't do that. Not a lot of people do, as the chemicals are not good to breathe, and sometimes if you leave it in these chemical baths for a long period of time, your print will actually melt, and it won't look like it's supposed to anymore as it's going in, because the chemicals will literally just start to melt away the plastic. So as I said, the filler and Bondo finishing, and then to give it a finished look over the paints, I would apply a gloss coat or a clear coat just to protect the paints, protect all the plastic that's onto it, and sometimes giving it that nice shine in the light. So going over a full print, so Iron Man mask, this is one of my most recent ones. So this is printing the actual side of Iron Man's helmet. That's the piece right here. So you can see that there's the back ridge, there's support material on the inside and on the exterior right here. So creating custom supports would have been ideal for this, as I wouldn't have wasted about 700 grams of a 1 kilogram spool of filament to create a 200 gram piece. This is what it looks like from the side of Iron Man. So it's the complete back and side of the helmet with the support material on the back and over the ears. And then that's what it looks like from the front on this one side. So it's adding all the support material for this overhang right here. It's ensuring that, because it wouldn't printed in midair, it adds support material from the base plate all the way up to that location, alongside with, of course, the ears and the actual back overhang. And then that's just a look from the bottom of the helmet itself, how it's stuck to the bed and the certain locations of the support material. And then that's the multiple pieces before. That's literally just after taking the pieces off the build plate. That's how Iron Man would have looked like if I hadn't continued with the post-production. So going more in depth, going with that, using the sanding, the Bondo, and the primer, you can start making it look like this. So I gave it a coat of green spray paint just to see the highs and the lows, sanded in between that, and then I added Bondo, which is this material here, because there were some little grooves, little deeper grooves that I wanted to. So I applied that, sanded to get it more smooth, and then once I had it to that location, I gave the entire coat just a little bit of Bondo over everywhere to get a nice, even coat to look and get to the finish that I wanted it to be, which is what you see in front of you after all the priming, the sanding, the Bondo, more sanding, priming, final paint, and then the clear coat paint. So that's how you can go from a actual printed object to a final object. You guys have any questions? Anything? That wraps up the knowledge section of the 3D printing workshop.
How many pieces is Iron Man?
How many pieces? So Iron Man printed with 2 ears, one on each side, the back of the neck, which is right here, a faceplate, a chin, and the back of the head. So for that, the last piece that you don't see here would have been the last piece, which is the white section right there. That's the final piece. I just haven't printed it yet just because it's bigger than this printer can handle at the moment, but that's okay.
There's just an error.
Oh, okay, we don't have to report for the questions. Yeah, that's good, thank you. All right, is there anything else?
Is this 3D printed?
Yeah, so this one?
Is it metal?
So this one's actually 3D printed as well. Yeah, this is 3D printed, and then after the fact I added more paint to it, just the white metal.
Because it
Yes,
looks like it's
completely 3D printed. That's 7 or 8 different pieces put together, and then using Arduino components that you can learn about out of 3D print. Our Arduino workshop included with 3D printing, you can get actual mechanisms that work together in unison. And yeah, so that's completely 3D printed. Anything else? Or anything you see that you want to learn more about? If not, you can also come up to me after the fact.